This lesson gives an introduction to long-term evolution, or LTE. In this lesson, you'll learn about the origin of long-term evolution technology, the motivations for the creation of LTE, LTE architecture, LTE components, user equipment identity in the mobile network, user equipment data flow, and an LTE roaming overview. Long-term evolution is used to identify the framework of the Evolved Packet System Architecture, EPC, which was introduced from the Third Generation Partnership Project, or 3GPP, in its Specification Release 8 in 2009. Its purpose is to provide technical specifications along with technical reports for a 3G mobile system, which its foundation is based on the Evolved Global System for Mobiles, or GSM core network, along with the radio access technologies that they support. It successfully gathers 7 telecommunications standards development organizations to provide a unifying cellular telecommunications network technologies by providing the foundational specifications for the technology. The organization is divided into 3 technical specification groups, which are Radio Access Network, or RAN, Services and System Aspects, SA, and Core Network and Terminals, CT. Its current focus is to shape the mobile systems and standards beyond 3G, which includes 4G and 5G technologies. Motivations for moving to a packet switch optimized system, known as long-term evolution, is to provide lower latency along with improved performance and throughput. No longer was there a need for both circuit-switched and packet-switched elements within the mobile environment, streaming the control plane, allowing for easier expansion and increased capacity. Reducing these network elements in the architecture also reduces costs and the number of core network nodes that operators need to buy and maintain. The air-defined LTE standard provides efficient data rates higher than what was achieved with older mobile technologies. Each base station, known as an Evolved Node Base Station, or eNode B, maintains its own radio control of its connected user equipment, abbreviated UE, and provides communication to the core as well as its adjacent eNode Bs. Both control plane and data plane can be scaled out independently based on need or coverage requirements of the environment. As mentioned, this too provides flexibility and cost-effective process when needing to provide capacity enhancements. Because LTE eliminates the implementation of a circuit-switched infrastructure like its predecessors, all traffic, including voice, is packet-switched with efficient throughput, allowing for transit time to be less than 10 milliseconds and setup times under 100 milliseconds. Because of these efficiencies, increased throughput and capacity is achieved. Enhancements to LTE through the years has provided improved throughput and additional features. Some notable LTE releases, along with their highlight features, were Release 9, which included location-based service, triangulation location services, Release 10, which provided LTE Advanced, the first true 4G technology, which included carrier aggregation and emergency service support, Release 12, which provided device-to-device communication for public safety, Release 13, accomplishing gigabit LTE and a stepping stone to 5G systems. It also identified benefits such as narrowband Internet of Things, or IoT, providing lower power capabilities, and the most recent Release 14, which was released in the middle of 2017, has a heavy concentration on the new 5G technologies. As expected, each new release provided many new enhancements beyond what was mentioned. For more detailed information about these releases and their feature enhancements, you can visit the 3GPP website. The LTE architecture is broken up into 2 sections. First is the Evolved Universal Terrestrial Radio Access Network, known as the EUTRAN. It includes what is known as Evolved Node Base Stations, providing the wireless connection for the user devices. Many of these are set up in their own geographical area using a specific radio spectrum, usually acquired or permitted by the local or national authority. As the user equipment, or UE, travels between these stations, the radio communications can be passed from eNode B to eNode B, providing the best possible connections. Along with all radio functions, which is isolated within each base station, they also provide signaling to the core, indicating a UE is requesting access to the network. They will also participate in control functions for UE mobility to and from the station. The second part of the LTE architecture is the Evolved Packet Core. It effectively provides the authentication and signaling, which ultimately establishes the data connections for the UE according to the eNode B it is connecting with. Both the control plane along with the data plane connections are established to and from the EUTRAN, providing service to the user equipment. Each component shown here has a specific function and are designed to provide efficient communication and data forwarding. These functions will be described in more detail later in this module. Collectively, these two areas make up the Evolved Packet System along with their various connections. Communications or signaling provides the ability to attach user equipment to the network and establish data flow to the device. Once the signaling establishes the data connection for the UE, it can now start forwarding or receiving traffic. Additional regions can be established with their own mobility management entity and serving gateway if needed, servicing their own eNode Bs, all having connections back to the same packet data network gateway and home subscriber systems. The signaling plane and data plane can be expanded independently, allowing additional base stations to be established in a region which can be serviced by the same Evolved Packet Core devices, providing scalability and efficient use of the elements within the Evolved Packet Core. Expansion of the network provides continuation of connection for the user equipment as it travels from eNode B to eNode B in between regions. Seamless handovers are performed while the user equipment maintains connection for phone calls or data forwarding. As the UE moves, signaling is performed to establish connection to the new eNode B, allowing the forwarding of its data to the new node. The old mobility management entity in the previous region will communicate with the next MME and forward the user context information. As shown, different regions can utilize their own mobility management entity and serving gateway again, providing scalability and capacity as needed, while the packet data gateway and home subscriber system is utilized by all regions being serviced by the mobile network operator. Each Evolved Packet System component has a specific purpose and, as you can see, unique required connections to other components. These connections can be data or signaling or both. Each connection is identified with a name and provides a specific function within the system. Note that not all components are interconnected and might only have a signaling or data connection to other components within the core. Let's look at each component and their function along with their connections in the following slides. The Packet Data Gateway, as the name applies, is the bridge between the packet data network and the Evolved Packet Core. This provides connectivity outside the EPC to the Internet or other services the network operator might be providing. The Packet Gateway provides IP assignment for a UE along with routing and NAT functions for data exiting or entering the EPC. The same IP address for a UE is maintained when it is attached to the mobile network, eliminating disruption in service, which would occur if a new IP was assigned while moving between eNode Bs. This UE IP address is not part of the subnets maintained within the EPC and is not routable within the EPC. Instead, UE traffic is encapsulated in a dedicated GTP tunnel, which is established during the UE attach process and establishes these tunnels towards the servicing eNode B. The GTP tunnel is established between the packet gateway and the serving gateway. For each UE will remain constant as long as the UE is connected to the mobile network or it roams outside of the serving gateway region. If this occurs, the new GTP will be established to the new serving gateway while maintaining the same IP for the UE. The serving gateway establishes and maintains the tunnels forwarding UE data to its eNode B it is being serviced by. This places the responsibility of forwarding to the correct eNode B on the serving gateway, relieving the packet gateway from this process. As a UE mobility moves it from one eNode B to the next, the serving gateway dynamically establishes connections to forward UE data. The serving gateway performs this process by the establishment of GDP tunnels to the proper eNode B servicing the UE. Each dynamic tunnel created is dedicated to that UE, and new tunnels are established if the UE migrates to the new eNode B. Tunnels are created between the packet gateway as mentioned before, along with an additional one towards the servicing eNode B. When these tunnels are established, they are associated with a unidirectional temporary ID, which is used to identify the UE the traffic is destined to. The temporary IDs allow for scalability along with a level of security, eliminating the need to have the tunnel associated with any sensitive UE identification. More details on the UE network identity will be discussed later. Signaling of these tunnels on the serving gateway are requested by its connected MME, which is responsible for authentication and coordinating and communicating the eNode B the UE is attached to. Let's talk more about the MME responsibilities. The Mobility Management Entity, MME, provides proxy support for the Home Subscriber System, HSS, along with the coordination of data path establishment within the EPC for the UE. It can be considered the traffic coordinator for most of the communication within the EPC. Because there is no signaling path from the eNode B to the serving gateway, all signaling, such as network access requests, UE mobility notifications, and all other coordination is managed through the MME. This provides centralized management of the local eNode B moving UEs seamlessly between nodes while allowing them to remain connected at all times. They also play an important part when a UE roams out of their home operator network, which we will explore later. Each eNode B under the MME signaling control will have an S1 MME connection to the MME. This provides two-way communication concerning the attach and migration of the UE. Information about the UE is gathered through this connection, which is known as the user context. This data provides the MME the guidance of what data paths are needed for the UE and will signal for their establishment. If the UE is coming from a neighboring region managed by a different MME, the S10 connection between the two MMEs provides notification and control signaling, allowing the continuation of the UE connection. During UE attachments, the attach request is sent from the eNode B to the MME. The UE identification is forwarded to the HSS for authentication, and if approved, the subscriber's service features, called the subscriber feature set, is returned. The MME is also responsible to control and notify the S gateway that the UE has moved to a different eNode B and to forward the UE data accordingly. Each MNO provider maintains their own home subscriber system, which houses a database containing all of their customer subscriptions. The HSS is responsible for responding to authentication requests from MMEs and providing the subscriber's capabilities in the network, known as a subscriber feature set. This information includes the services the UE is subscribed to, which could include voice, data, or SMS. Additional services such as unlimited video streaming or free mobile-to-mobile calling could be part of the subscriber features. This component of the EPC remains in the MNO's network and has connections to each MME the provider owns. It can also have additional connections to other reciprocal MNOs, providing authorization if any of their subscribers connect outside their home network. Authentication of user equipment is identified within the EPC by their International Mobile Subscriber Identity, abbreviated IMSI number. This value is presented to the HSS for authentication. However, it is only used for initial attachment of the user device. Once authorized, the temporary IDs associated with the UE's tunnel are used within the EPC. This provides security for the sensitive IMSI ID, minimizing exposure. We will see more about this identification in a moment. The evolved node base stations bridge the wireless barrier communication from user equipment to the wired connection back to the EPC. Each eNode B manages and operates its own radio access network, providing radio connectivity to devices within range. As UE devices attach to the network, the eNode B accepts tunnel requests being established by the S gateway to provide UE data forwarding. eNode Bs generally have physical connections commonly known as backhaul networks, providing connectivity back to the EPC. These backhaul connections leverage the local exchange carrier, or LEC, or some other local internet provider. From this physical connection, logical connections to the eNode B consist of the S1 MME, which provides the needed signaling communications, and the S1U connecting to the S gateway. The X2 connections provide the ability to perform a handover of UE to a neighboring eNode B and forward already received UE packets while the new GTPU tunnel is established to the new eNode B. These X2 connections, although commonly present between adjacent eNode Bs, are not mandatory. Mobility can be achieved via S1 connections between eNode Bs via the MME. UE consists of mobile or terminal equipment capable of communicating within the designated radio spectrum of the carrier it chooses to subscribe to. Within the mobile, there is a Universal Subscriber Identity Module, USIM, housing the identity that will be used as the identifier within the network known as the International Mobile Subscriber Identifier. Without the Subscriber Identity Module, or SIM, installed, which houses the IMSI, the UE equipment can only provide emergency call services. This UE identity allows for subscriber services to be associated with the device. Other identities are associated with the mobile devices but are not used for network identification. These include the International Mobile Equipment Identity, IMEI, which is a unique identifier of the device similar to a serial number. This number, like serial numbers, can be used to identify stolen equipment for inventory purposes. As mentioned, International Mobile Subscriber Identifiers are contained within the SIM card, which is installed into the user equipment, providing the ability to uniquely identify the devices on the network. This identity, however, is a conglomerate of identities providing insight of the UE or SIM's origin, which is country, along with its home network, the provider, and lastly, a unique subscriber value. The first 3 digits of the IMSI provides the country of origin. Countries such as the United States have multiple mobile country codes, MCCs, due to capacity requirements and expansion. Next is the 2 or 3 digit Mobile Network Code, MNC, identifying the provider within the country. Like with the MCC, carriers within a country can have multiple mobile network codes, which in some cases identify different types of network capabilities, including older 3G networks. These 2 values, MCC and MNC, make up what is known as the Public Land Mobile Network ID of the provider. This PLMN ID is a common term that is used often in the standards set forth by the 3GPP organization. Lastly, a unique number known as a Mobile Subscriber Identification Number, consisting of 9 or 10 digits, complete the IMSI, which is then used as the identifier of the UE equipment virtually anywhere in the world. This helps MNOs quickly identify that a connecting UE is a roaming device or a local subscriber. Additionally, if they are a roamer, it allows the MNO to identify the home network of the UE to obtain authorization of the UE attachment request sent by the UE. As mentioned previously, GTP tunneling is established providing the forwarding of user data within the LTE network. This process provides the ability for the UE to maintain the same IP address as it moves between eNode Bs. This eliminates disruptions that would be caused by the renewing of IPs during UE movement. These tunnels are dynamically established through signaling between the eNode B and MME. This signaling occurs either when the UE sends an attached request or for UE mobility. Once authorized, the MME signals to the S gateway to establish a data path, GTP tunnels, for the UE data. The S gateway receives the tunnel request and then forwards the request onto the packet gateway to assign an IP and establish a tunnel back to itself for the UE data. The GTP tunnel establishment request is sent from the packet gateway, which includes a unique tunnel identifier indicating the UE it is to be used for. Next, the S gateway sends a tunnel request to the eNode B the UE is attached to, completing the data path for the UE device, allowing it to forward and receive data. Because of UE mobility, it may become necessary for the UE to be serviced by a different eNode B. When this happens, the source eNode B sends a handover request over the X2 connection to the target eNode B. Once confirmed, the source eNode B will forward any existing data for the UE towards the target eNode B, while at the same time the target eNode B signals the MME of the movement. The MME will then signal to the servicing gateway to establish a tunnel to the target eNode B for the UE data. Once the tunnel is established, direct forwarding of UE data can be sent through the target eNode B, and the source eNode B tunnel for the UE can be discontinued. UEs roaming out of their home network is a big part of the design of the 3GPP specification. UEs are designated to be able to communicate on many frequencies, allowing it to connect to MNO's networks all over the world. With that said, the RF connection of the UE is not the only requirement for successful roaming. Reciprocal agreements, along with connections between the visiting network operator and home operator, are needed to allow for authentication and usage tracking. The agreement and the visiting network operator's proximity to the home operator affect the way UE data is forwarded towards its destination. Visiting networks can be in the same country where home carrier coverage is not available, or in a different country where the home carrier does not provide service. Either way, the authentication request of the UE is sent to the home network operator. However, the routing of the UE data traffic can be different. The most common ways that user data is forwarded when a UE is roaming outside its home network is by either a home-routed or local breakout design. The home-routed design is the most common between MNOs. With the home-routed configuration, the UE data traffic is tunneled to the home operator's packet gateway for forwarding. By doing this, verification of data use of the UE is monitored by both providers. With this design, billing for data use can be monitored in the packet gateway of the home operator, as well as the visiting network's S gateway. With UE data being forwarded to the home operator from the visiting mobile network operator, this ensures that both have verifiable data usage of home carrier subscribers. With this design, careful planning is required to avoid call latency, and distance between the MNOs has to be considered. Local breakout is another design used between MNOs. Advantages of local breakout is efficient routing to the Internet and that voice traffic has the lowest latency. This is especially effective when the visited MNO is very distant from the subscriber's home network. With this design, however, because the home MNO is not able to monitor the data use of their roaming subscriber, the home MNO will have to trust the visiting MNO's usage reports for billing. Thanks for taking the time to view this training.